Hello, my name is Gabriel Weindl, and this is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. The current talk will be about how we can assess model-based inferences in decision-making using single-trial response time decomposition.
A decision can be described both by the favored option and the time used to make the decision we usually refer to as the response time. In what we call cognitive modeling of decision-making, these two features are jointly considered into a mathematical formalism to generate inferences about the mental organization of decision-making. The most prolific model in decision-making is arguably the drift-diffusion model. The core structure of the DDM and many other decision-making models is that response time is decomposed into a decision time, the time when the decision-maker is actively taking a decision, and a non-decision time, which would be, as the name suggests, all the time left that is not dedicated to deciding. If we concentrate around this decision time, the core idea is that when faced two alternatives, the decision maker is going to accumulate evidence in favor or disfavor of each alternative. The accumulation of evidence is represented by this stochastic path. The more evidence comes in favor of one alternative, the more this path will be drifting towards the alternative favored by the environment, indexed by the parameter of the model, V here. The path stops at a given amount of evidence, variable across tasks and participants, represented by the parameter A. The non-decision time is then the parameter indexing all the residual time. Now, the main advantage of DDM is that its parameters are intended to be interpreted as psychological processes. For example, the drift rate is supposed to index the ease of processing of our participant. The threshold is linked to the quotient of response, and finally, the non-decision time, often referred to as the encoding response time, is, as its new name suggests, considered to be the sum of the times the participant needs to encode stimulus and the time needed to execute the chosen response. Now, this interpretability of the parameters is of high interest for a lot of researchers and clinicians, as we can make inferences directly on these cognitive processes. But in order to draw such second-order inferences from variation of the model parameters, one has to ensure that the parameters do measure the intended cognitive process. To validate such interpretation, there is one gold standard, using an external measurement of the latent psychological process. If one can find a measurement that has a clear linking function, namely that the measure is undoubtedly linked to the given process, then we can validate the interpretability by testing for the recovery of that measure, ideally with single-trial precision, by the model parameters. In this study, we are using such a linking function to probe the validity of the inference drawn from a decision-making model such as the DDM, but we are going to focus specifically on one parameter, namely the non-decision time, so the sum of the processes used to encode the stimulus and to execute the chosen response. And we do have a measure that has both a single-trial precision and a clear linking function with the response execution time, namely the muscle activity derived from the electromyogram of the responding muscle. Electromyography is a technique allowing to measure variation in electrical potential of muscles. Hence, when a participant is placed in a decision-making task, we can, by using two electrodes for each responding muscle, record time points at which the muscle was active. This technique gives the following recordings, which is an example of one trial of a real participant. Response time is defined as usual as the time between display of the stimulus and the response recorded by the computer. We then detect the onset of the EMG burst and decompose the response time into one premotor time, noted PMT, the time between stimulus and before the EMG activity, and the motor time, the time between EMG onset and the recorded response, noted motor time or MT. When we perform this decomposition for each trial of a decision-making task, we obtain distribution for response time, obviously, but also for premotor time and motor time. So this is an example for one participant. Now, the linking function is easy and was already suggested by Duncan Luth 40 years ago. The time from that event, he was referring to EMG onset, to the response, is a proportion of the entire motor time, T response here, and that in turn is a proportion of the residual non-decision time. Our assumption is then clear. MT is at least a subset of the model time to execute the response, which itself is a subset of the non-decision time, which is the parameter we are actually estimating. Hence, we can ask the following questions. What experimental manipulations affect MT? And then how EMG decomposition, PMT and MT, relate to the model parameters? with two distinct hypotheses. If PMT and MT capture distinct processes, encoding and deciding in PMT and response in EMT, we then expect an independence between both measures. If MT is a subset of, and then the second hypothesis, if MT is a subset of non-decision time, we then expect that the measure of MT will be proportional to the estimated non-decision time by the parameter. To that end, we designed a standard decision-making task. Participants were presented two Gabor patches and had to choose which one was the most contrasted. Here it is on the right. They responded either with the left or the right hand depending on the chosen patch. And in order to test the effect of experimental factors on motor time, we recruited 16 participants in the first experiment and manipulated blockwise the SAT, speed accuracy trade-off. Either participants were asked to favor accuracy or the speed of that response. And in addition, we also manipulated the stimulus difficulty by increasing or decreasing the difference in contrast between both patches. We then tried to replicate the results in a second experiment with again 16 participants, but this time, however, we reduced the force required for the participant to produce a response, and we were then closer to traditional task response execution settings. After evaluating the effect of experimental factors, we tested the independence between MT and PMT by computing the correlation between both measures. We then fitted a hierarchical drift-diffusion model using bitrial motor time as a regressor on non-decision time to test for the proportionality. So a quick side note on the statistics used. For the analysis, we relied on hierarchical Bayesian methods, allowing us to estimate population parameters, for example, the effect of SAT on the motor time. And second, using Bayesian analysis, we have posterior distribution rather than point estimates for each parameter, hence the probability of a given value of a parameter, knowing the data, the model, and the priors used. Therefore, we used linear mixed model for the factor effects on MT and hierarchical Bayesian estimation of drift-diffusion model parameters using HDDM. So first, looking at the effect of experimental factors on MT, the raw data are presented on the left, contrast level on the x-axis, mean MT on the y-axis. When accuracy is favored, it's the left column, and when speed is emphasized, it's the right column. And the distinction is also made between correct and incorrect responses, respectively in green and in red. The second experiment, raw data, is in the small insets with the same design. The plot on the right represents a subset of the mixed model coefficients, which are read like linear models. To simplify, I just simply removed the interactions to ease the presentation, but the whole analysis can be found in the preprint. What we see is that MT, motor time, is highly sensitive to speed accuracy trade-off, with an effect size across both experiments around 15 milliseconds. More surprisingly, we also see a coherent and robust effect of contrast when the response is correct, with an effect around 6 milliseconds, suggesting that the difference between the hardest and the easiest stimulus difficulty level is approximately of 6 milliseconds. We see it across both SAT conditions and for both experiments. Now, one last result is even more surprising, as we observe a difference between a correct and an incorrect response, where it would be around 5 or 6 milliseconds, meaning that incorrect responses are slower than correct ones. So this does show us that motor time is variable in all factors considered in this experiment. We then computed the correlation between PMT and MT. However, we do so by splitting across SAT conditions and PMT quantiles. The reason being that it is likely that the speed at which decisions are taken might change the covariance between processes contained in PMT and processes contained in MT. Doing so, we see that PMT and MT are mostly uncorrelated, as the correlation values computed for most quantiles are inside the 95% confidence interval. This null confidence interval was obtained by applying the same method to compute correlation on two random variables, and is represented by the gray shaded area. However, in both experiments and in both SAT conditions, we see that the first quantiles, and the quantiles at which the decision was the fastest, present a negative correlation between PMT and MT. So we interpret this as evidence that all trials might not be generated by the same model. So we then fitted a drift-diffusion model, so this is a rather complex figure for which I would need more time to describe it fully. but it shows how the DDM predictions, the small dots, fit the data, the crosses. So this mainly shows that our model does fit the data pretty well. Now when we add the bi-trial motor time as a regressor on non-decision time, we see that the posterior distribution in both experiments lies around 0.1, 0.4, with a mean around 0.28. This suggests that an increment in MT motor time of 1 unit, for example milliseconds, is associated with an increase of 0.28 unit on non-decision time. So this first suggests that we have a link, rather weak but still important, between motor time and non-decision time. But if we look at the estimated standard deviation of the MT regressor, we see that it is rather high, suggesting that some participants have a higher link between MT and non-decision time and that others are closer to 0. So there could be some inter-individual characteristic mediating the link between MT and non-decision time. Now we had the idea to connect the result on deviation from DDM, as shown by the negative correlation between PMT and MT, and this inter-individual difference in the link between MT and non-decision time. Therefore, the last question, does the inter-individual variation in the PMT-MT correlation co-vary with the variation in the link between MT and non-decision time? So this figure shows for both experiments the scatter plot for the mean correlation between PMT and MT on the x-axis, and the corresponding link between MT and NDT and non-decision time on the y-axis. Now to compute the correlation, as we have posterior distribution and hierarchical estimates, we cannot use a simple correlation, but we can use plausible values. The small subplot shows the distribution of correlation using the plausible values, and we see in both experiments that the correlation between both variables is positive and likely rather high, suggesting that the more negative the correlation between PMT and MT is, the weaker will be the link between motor time and non-decision time. Finally, in conclusion, first, the response execution time measured with EMG is sensitive to a lot of factors. This implies that response execution is not a ballistic movement insensitive to experimental manipulation. Second, concerning the correspondence between EMG and DDM decomposition, processes contained in PMT and MT are correlated only in a small fraction of the trials, suggesting that a fraction of trials may not be generated from the processes hypothesized in sequential sampling models such as the drift-diffusion model. And we do see that non-decision time co-varies with the external measure of response execution, that is, motor time. This all shows that there is a meaningful correspondence between DDM and the MT decomposition, suggesting that non-decision time does measure the intended cognitive process of motor execution. However, inference validity from non-decision time about motor processes depends on the amount of trials that present a deviation from the DDM, and hence inference validity probably varies with participants and probably also task demands.
So this is the end of the talk. I leave links in the description for the OSF repository, and I hope to see you on the discussion board, or even, although it's going to be late for me, at the question and answer session organized the 19th of July between 5 and 6 p.m. EST. Thank you for your attention.